Hello everybody. Welcome to our lecture for this week, Fire as a Physical Process, or really what we're going to talk about is the science behind wildfire and how fire actually works and all the different components of fire. So lots to go over in this lecture, so let's kind of just get started. So the quote that starts this chapter off in the book is, "Where there's smoke, there's fire." And it's something that you've heard a lot, but there is a reason for it. There's a reason it all works together and comes together and makes sense. And that's really what we're discussing here today is that whole process of how does this actually work? How does this all come together? Why, when there's smoke, is there fire? So let's kind of start at the beginning with kind of the easier stuff. So in this class, it's wildland fire ecology. So when we say wildland fire, what do we mean? Well, when we talk about the wildlands, we're talking about uncultivated land. So really, anywhere that's not farmland, anywhere that's not urban, that's our wildland. So that's the wildland part of it. The fire part of it, we're going to go into depth for the next hour or two, really getting to what fire means and what fire is. And then ecology is the study of wildland fire and how it interacts with the environment and all the different pieces and components of the environment. And we're going to definitely get into that when we get into the fire behavior section a little bit later in this lecture. This is a good time to pause and take a look at this YouTube video that I've posted here to kind of give you just a little bit more background on the idea of wildland fire. So, with the idea of wildland being uncultivated land, what is fire? Fire is a rapid release of the heat energy stored by photosynthesis. So we have the photosynthetic process in which we get energy from the sun, and it goes into our producers, which are our plants, and then they're able to transfer that energy up the food chain. Well, what fire does is it releases the heat energy and that energy that has been stored by photosynthesis. It's a manifestation of a chemical reaction. So fire is it's this radiant energy from the sun. It's been transformed to stored chemical energy. Then when the vegetation burns, it goes thermal radiant. It becomes thermal radiant and kinetic energy. So why is wildland fire important to understand in California and the western United States? Specifically here in California, it's really due to our Mediterranean climate. So we have hot and dry summers and cool and wet winters, or at least when everything's going normal with our climate, that's what it's supposed to be. Hot and dry summers, cool and wet winters. And so that is not conducive at all to decomposition. So when you have photosynthesis, to have a nice healthy ecosystem, you have things that grow, and then when things are done growing, then they die off and other things can grow, and the ecosystem keeps replenishing and everything works well, a nice functioning system. Well, out here in the Mediterranean climate, decomposition does not happen well. It's not a climate that's adjusted well to decomposition, because when it's warm, it's too dry for things to decompose, and when it's wet, it's too cold for things to decompose. So there's a very short window where decomposition can actually happen. So decomposition rates are very slow out here in California, so you get a buildup of accumulated organic material or accumulated biomass. And because you get this buildup and accumulation, there needs to be something else in the ecosystem that then cleanses the ecosystem and restarts the ecosystem and keeps the ecosystem in check. And that's those good fires that we've discussed before, is the idea that fire kind of just picks up the void left by decomposition. So fire has a role in our ecosystem, and a very important role in terms of kind of restarting the ecosystem and cleaning the ecosystem and allowing the ecosystem to function properly. So another bit of terminology you'll hear about is the combustion process. So combustion is just another word for fire. So this energy releasing rapid chemical reaction at high temperature that can become self-perpetuating. That is just fire. You know, whether we say the physical manifestation of a chemical reaction or the energy releasing rapid chemical reaction at high temperature that can become self-perpetuating, that is fire. That is what it is. And so the combustion process is the idea of things actually catching on fire and this transfer of energy. And so kind of trying to put it all together in terms of the idea of this energy transfer. So we get the plant material produced by photosynthesis. So you get carbon dioxide, water, and the sun's energy combined to produce cellulose, lignin, and other components. So you then have oxidation, which is the reverse of photosynthesis. So that process either happens through decay, which is through the process of decomposition, or through fire, which is just this rapid release of energy. And so we can kind of see right here, you got stored chemical energy here. You get a chemical reaction with oxygen and heat, and then you get this rapid release of thermal energy, which is fire. So this is the one process of taking in energy, and then the one process of giving off energy. So photosynthesis, radiant energy, is transformed to stored chemical energy, and then when you have a fire, chemical energy is transformed to thermal and radiant energy. Just kind of looking at it again. So the process of decomposition versus the process of fire. So we get photosynthesis coming in either way. We get some cellular respiration, which is just, you know, the idea of the plant growing and using energy. The fall in plant material and all the stuff that's not getting used will get decomposed and cellular respiration. Or you might get combustion, and you have the big process of combustion happening. So those are the ways we get in energy and the ways that we can lose energy in the system. The one we're going to focus on, though, is the fire aspect of it. So how do you get fire? How does it actually work? Is there a good spot for me? How about here? All right. How do you get fire? So you need to talk about the fire triangle: fuel, heat, and oxygen. Fire requires all three of those things: fuel, heat, and oxygen. And then you'll see down here in the center it says chemical reaction, because it's the idea that you get all three of those, and then it's the combination of them in the chemical reaction that is the fire. And when we're talking about fire control or fire management or any of those things, when what we're really talking about is the idea that we're going to take that fire triangle and we're going to break one part. We're going to get rid of the heat, we're going to get rid of the fuel, we're going to get rid of the oxygen. One of those things has to disappear. Now, if you really think about it in terms of fire control, oxygen, it's always in the atmosphere. It's going to be pretty hard to get rid of that one. Heat, if it's the middle of summer in Bakersfield, are you going to be able to get rid of heat really easily? Probably not. So the one that's going to get focused on a lot more in terms of fire control, and where a lot of the fire science is going to focus on, is the idea of fuel, because that's the one, the burnable material, the stuff that the fire needs in order to keep going. That's the one that we can kind of control. That's the one we can get rid of. So that's the one that's going to get focused on. And so kind of breaking it down a little bit more on the right hand side here, this science of a wildfire. So you got oxygen. You need 16% oxygen. Our atmosphere just normally has about 21% oxygen in it. So there's always enough oxygen in the air for fire to be started. The heat allows fire to spread by evaporating fuels. It's basically just a drying process. When you have heat, all it's doing is getting rid of the moisture. Whenever the moisture's gone, stuff cooks. It's also the same way if you think about the process of just cooking in a kitchen or defrosting. What you're doing is you're getting rid of the moisture in something and allowing it to cook. That's why when you cook meat and things like that, sometimes the meat will be moist, and sometimes if you burn it, if you burn the crap out of your food, what does it taste like? It tastes super dry. it tastes super like there's nothing in it, because what has happened is that heating process has taken all the moisture, all the juice, all the kind of good stuff out of there, and you're just left with this hard brick of whatever's left over. The same thing happens to the fuel. It really is the same process when you're burning fire. There's nothing different between what's happening in your stove and what's happening in a wildfire, other than, you know, meat and veggies versus grasses and trees. And then, so our fuel, that's our third part of it to make our chemical reaction of fire. The fuel is the burnable material. The fuel is anything that can catch fire or can, with enough heat put on it, lose enough moisture to then catch fire. That's why whenever fuels get dried out here, we see, you know, we're driving down the highway and we see big, huge patches of yellow-brown grass as opposed to the green grass. Everybody gets worried that the fire danger's up higher. Why? Because there's less moisture or no moisture in those fuels, meaning they're really, if you get some heat, you know, the oxygen's always in the atmosphere, we can get fire really easily. When they're green, at least it's going to take a little bit more effort. It's going to take a lot more heat to really get it going. But that doesn't mean green fuels can't burn. They can burn. You just have to give it more heat. So kind of just even breaking it down even more in terms of the fire triangle. So heat sources, open flames, the sun, hot surfaces, sparks and arcs. A lot of fires that you see like on the side of the freeway is, you know, a cigarette being thrown out the window, or some sort of friction or arc with an arc with a power line, or friction with you know, a truck driving down the road and dragging chains and sending off little sparks. And you can get compression of gases. You can get all sorts of different heat sources. Like I said, the atmosphere already has about 21% oxygen in it. And then the fuel, this is what happens to get all sorts of other things burning. But for us, it's really a focus on woody fuels and grass. And we're going to spend a lot of time talking about the actual fuels, the actual materials that burn, that are necessary for fire in the wildland. Just get myself up here. So in terms of oxygen, how does a fire breathe? Well, oxygen is very reactive. So it's ready to react chemically with other molecules. And oxygen is maintained in the atmosphere by the balance between photosynthesis and respiration. But really, the big part is oxygen molecules are kind of, I don't know, the best way I think of to describe oxygen is like, you always, if you go out, you know, you always have like some friends who are like, I don't really want to do anything. And you got some friends who are like, yeah, man, sounds good. And then you've got a friend who's like, yes, I am down for whatever. Let's do it. Let's go. This is it. I want this. Let's do it. There always is that friend. Oxygen is that friend. Oxygen is very reactive. It's ready to go at all times. It is just fired up at all times, ready to go, and just looking for something. And then all of a sudden, if something happens, boom, fire. And that's what oxygen's job is there. I know for us, we think about it, oxygen is there for us to breathe. But oxygen, in terms of the idea of a fire, oxygen's that thing that's there and it's ready to go, and it's just kind of sitting around just waiting for something to happen. In terms of fuel, fuel is the source of heat that sustains the combustion process. In most fires, combustion is incomplete and not all of the fuel is consumed due to lack of heat, and it will vary due to the moisture content in the fuel. So that's why when you see, I know we see these mega fires lately, so we kind of think of like everything just being moonscaped and wiped out. But in most wildland fires, what you'll see is you'll end up seeing like a mosaic of some areas that got really burned, and some areas that barely burned up at all, and some areas that burned just the way you wanted it to. And it's due to the amount of heat or it's due to the amount of moisture or some combination of both. You'll hear a term, moisture of extinction. What that means is that's the level when there's too much moisture in the fuel for combustion to occur. So if a piece of fuel is at the moisture of extinction, that means that no matter, how much heat you put on this thing, it's not going to happen. There's just too much moisture in the fuel for combustion to occur, right? If I even if I send a rip-roaring fire, if I've got some reeds that are, completely soaked in super cold water in a lake, as soon as it hits that, there's just too much moisture there. It's not going to happen. It's not going to burn up. Sometimes it will. It really depends on how much heat and what else is going on. In terms of our heat is just thermal energy. It's the energy of molecular motion. So it's energy in transit as a result of a temperature difference. Okay, well that sounds fancy. Let's see if we can simplify it. So when we say temperature, we're saying the temperature of a substance is a function of the kinetic energy of the motion of its molecules. So we're just saying the weight, how fast or slow the molecules are moving is the temperature. Well, what do you mean? So when we look at this graphic here, and remember we're talking about heat, we're talking about temperature. So kinetic energy increases as temperature goes up, right? So these molecules are moving around, they're bouncing around, they're moving, right? Kinetic energy decreases as temperature goes down. So look at how big this arrow is and how far they're going and all that. And now we're barely moving. We're not going that far. We're not going to be bouncing around. See, these molecules are bouncing around. They're hitting each other. So that motion, that is making the temperature rise. Whereas when it's cold, these molecules don't want to move. Just like when you're cold, you don't want to move. You don't want to go anywhere. You don't want to do anything. And so then that kinetic energy goes down, and therefore it's not as hot. It all kind of plays together. And so what happens is you've got these molecules moving around. When it's hot, remember we got oxygen. Oxygen's ready to go at all time. So if we get the kinetic energy really moving, it's really hot, and then so we can get these fuel particles moving around. We get the oxygen particles moving around. Bam! Now we got combustion. Now we got fire. Now we're giving off heat. We're giving off exhaust. We're giving off particles and smoke and all that. And now we can supplant more heat and kind of keep this thing going and have it become this self-perpetuating thing. And this is how we get a fire burning. So with this combustion process, we've got 3 phases. So we're going to have preheating, we're going to have the gaseous phase, and we're going to have the smoldering phase in terms of our combustion, in terms of our fire. So the preheating phase, so the fuel ahead of the fire is heated. I know it says R, sorry. Every once in a while you'll find a mistake. The fuel ahead of the fire is heated and brought to ignition temperature. So hydration is raising the water in the fuel to boiling temperature, evaporating the water, and then heating water vapor to flame temperature. So that's a dehydration process. And so what we're talking about with this preheating phase is we're really just getting the water, getting the moisture, getting the water vapor out of the fuel. So if you look at this graphic on the right, so this part's already burned. This part is the part that's burning right now. This preheating phase is happening over here where all this water vapor, all the moisture is leaving this thing so that this thing can then catch fire and be ready to catch fire as soon as this flame decides to just kind of keep pushing and keep giving it that heat, and so that it can move on. Fire can't move unless the moisture has gone down to a certain level. Once it's gone down to a certain level, the fire can then move forward. So this preheating phase is important because that's how it dehydrates. That's how it makes the fuel ready and available. Makes the fuel available fuel for the fire to burn. You also have pyrolysis happening at this time. So that's a thermochemical decomposition of the wood. So the temperature needs to be raised to a certain point to make gases start to volatilize and then vaporize. So that is also happening in this preheating phase. Pyrolysis is happening the whole time in all of this, but it starts in the preheating phase and then keeps happening during the other phases of combustion. During the gaseous phase, let's see here. I don't know that there's a good place to stick me. Maybe I'll just go right here. Okay, the gaseous phase starts with ignition. So if you say to yourself, well, wait a minute, how did the first phase happen if the fire's not going? Remember, ignition happens, when we say ignition, we're just saying the temperature where a source is no longer required. So ignition happens on the different pieces as the fire burns through. And so this gaseous phase is when active burning begins. And so if we go kind of back, let me go back real quick to this other picture here. Remember, this part is not on fire yet. This part has not ignited. So as the moisture and everything leaves here, and now it's gotten to the moisture level that this heat can now pass through, now we get ignition happening over here. So when we say ignition, we're not just talking about just the start of the fire. We're talking about any time any part of the fire moves along or the fire kind of ignites something new. Once ignition temperature is reached, gaseous combustion begins. So oxidation is initiated and the active flaming front develops. The flames come from the burning of distilled gases. So you get water and carbon dioxide given off, which is not surprising because remember, we're still doing that kind of reversal of the photosynthetic process as things burn. In the smoldering phase, so our third phase of combustion, the surface of the wood is burning instead of the gases above, right? So preheating, we're drying everything out, we're volatilizing gases, we're getting everything ready. Then we've got the ignition phase where we actually get, we're getting the gases on fire and getting this, and everything's ignited and ready to go. And then the smoldering phase, now we're actually getting into the wood or the grasses and really breaking down the chemicals inside of the fuel or the material. Charcoal and other unburned material will remain after the flaming front continues to burn. Eventually, if it gets down far enough, it'll leave ash, so you can kind of see the idea of charcoal and ash in this picture here. Temperature and heat will be released are less, can be less than a flaming fire in this smoldering phase. So what's interesting to me is that in the smoldering phase you get low rate of spread, and we'll talk about rate of spread in detail in the fire behavior part of this lecture. But what's interesting is because you get a low rate of spread, that is actually a bad thing. You would think of a low rate of spread, so the fire not moving very fast, you'd say, oh, well, that's a good thing because then we can manage it and all that. Yeah, but think about this picture right here because I used it specifically. So that fire is not going anywhere. The fire is not really going to spread out and, become some mega fire or anything like that. It's pretty contained. But that fire in there is so hot and those things are so on fire. And it's just going to keep burning and burning and burning. And you can put, and I've had to do this myself, you can put a lot of water on it. I did a tree a few years back when I lived in Georgia and was doing a prescribed burn. There was a tree that I think I put like maybe 10 gallons of water on one tree. And thing was still smoldering, still burning because it was so deep and so hot. And there wasn't much I could do about it. But what's problematic with the low rate of spread is that, yes, it won't go anywhere, but that fire is still burning stuff. So when I say it doesn't go anywhere, we usually think about the idea of fire spreading out along the surface. But that fire is burning down, and it's burning roots, and it's burning soil, and that can be just as much of a negative as fire spreading out and burning a lot of things. It really depends on what you value and what's important, because the damage to the soil that you could have with some of these deeper fires, the damage to the roots, you could end up killing the tree, whereas if you had kind of a quick fire burn through, the tree might barely feel it, whereas if you get one of these fires with a lot of smoldering and this low rate of spread, you might actually kill the tree, because the fire basically just sits there and burns and burns and burns and burns and burns, whereas it might have only burned for a couple minutes in this quick moving fire. You also get carbon monoxide released, which is definitely bad. Carbon dioxide, not as bad. Carbon monoxide, really bad. Smoldering can last days or weeks with considerable fuel consumed and smoke produced. It kind of depends on, how hot it gets and what kind of material you have, how wet it gets, all those things that play into fire. Remember, in terms of fire control, when we're talking about trying to manage all these things, you gotta get rid of fuel, heat, or oxygen. Think about trying to get in here and get rid of the fuel. That's going to be kind of hard, because I'm going to have to dig these pieces of charcoal and whatever left of this wood out. But there's only so much I can dig out. If it starts burning down into the soil underneath, I'm not going to be able to dig out the fuel. Well, then I got to get rid of the heat. Well, I can pour water on it, but if I can't get enough water in there to get rid of the heat, I can't get rid of the oxygen. So it becomes really problematic and can be hard to deal with in some cases. So kind of summarizing combustion. So it may or may not involve a flame. You can get volatiles produced during the preignition phase that will then ignite a visible flame. After the flaming combustion has burned most of the volatiles, those gases, that's why it's that gaseous phase, the remaining carbon may burn as a solid by surface oxidation, and that's our smoldering or glowing combustion. So just kind of giving this idea of, we're looking at just this idea of heat and fuel and time that gets us our ignition, and then you can get your weather effects, you can get topography and other things in there. In terms of our combustion, so you've got unburned fuel up here. Here's where our flaming combustion, try and make it look more like a wildfire than just a little bit of fire going. So back here we've got our glowing and smoldering combustion. Here we've got our flaming combustion happening, and here's our unburned fuel. So we get that preheating, that dehydration of fuels happening out here. Here's where our gases are burning off, and back here is where things are really just still cooking and really having that smoldering combustion happening. Here's just another look at it. So here's our fuels that are getting pre-ignited. Here's our fuels that are doing flaming combustion, and our smoldering combustion is happening back here. These smoky, anywhere where you see these smoky areas back here, that's smoldering combustion. These glowing embers back here, that's also smoldering combustion. Some people call this smoldering and glowing. It's all just smoldering. And then I've got this link right here to click on, where you can kind of see what it looks like inside of a fire through some cameras that were set up. So I would say pause the video and take a look. So during combustion, fuel is then converted to heat. Some of the mass is released in smoke. That's why when there's smoke, there's fire. So that's that ties us back to what we started this whole talk with. The fine fuels are consumed in the flaming front, and we're like I said, we're gonna focus on fuels a lot in a little bit. But when we say fine fuels, we mean small, easy to burn stuff. So dead grass, pine needles, or what we call conifer needles, or conifer leaves. They're needle-shaped leaves, small twigs, things that can really easily get dehydrated, get broken down, and then burn up pretty easy. Usually, depending on the fire, branches usually are mostly consumed unless they're really big branches. And then the other stuff will either get consumed or partially consumed after the flaming front has passed. So in that smoldering, glowing phase. So just to give you one more example, here's the idea of campfire and the idea of combustion in terms of a campfire. So you get your fuels set up, you're going to preheat them, maybe you use some kindling or something else, and you set up your fuels so that they're easier to burn. You then get the smoke going, and in that smoke, those are your gases. You're getting to that that ignition. You get, oops, sorry. There we go. We get that ignition happening, right? We get some glowing combustion happening at the bottom. We end up eventually getting to a lot of smoldering happening, and eventually our fire starts to weaken. Our fire is mostly out because our fuel is disappearing, and then finally we don't have enough heat, we don't have enough fuel, and the fire goes out. So then we're going to pick it up in the next video with heat transfer.